welcome to another episode of Momentum Malum Interviews. Today we'll cover Dr. Martin O. Bohn. Care to introduce yourself?
Oh yeah, so as you already said, my name is Martin Bohn. I'm a corn breeder here at the Crop Sciences Department at the University of Illinois. And yeah, as the name suggests, I'm a corn breeder. That means I am developing corn for, specifically in my program for organic farming systems. And but we are also interested in some more basic questions related to corn. For example, we are investigating how the genomic structure of corn can be used to make genomic selection in breeding programs more effective and efficient. And we are also investigating how the microbiome in the soil is interacting with corn plants and corn genotypes. And we try to utilize that information to develop corn that is more effective with taking up nitrogen. And yeah, so we have a well-rounded research project here in my group, from something that is very basic research, looking at the structure of genomes, and we try to apply that in a very basic, not very basic, in a very applied research program for the development of corn hybrids in an underserved community that is organic farmers that produce corn.
Excellent. So let's start with the two broad questions then. You mentioned in your paper on the topic of native resistance to Western corn rootworm. What are the mechanisms of resistance found in these native corn germplasm specimens?
Before I answer that question, let me tell you that I was actually pretty surprised that after more than 10 years, somebody is really interested in Western corn rootworm native resistance, so the resistance that the plants show on their own, plants that are not transgenically modified show some resistance. And because in Western corn, for Western corn rootworm protection, the industry is using transgenics, and that's kind of the mode that all companies try to tackle that problem of Western corn rootworm. But 10 years ago, that wasn't kind of in the making. There were all kinds of issues with regard to Western corn rootworm and transgenics, and there were open questions with regard to the resistance management of GMOs, that people were still interested in looking into some native resistances, so some natural resistances of corn against Western corn rootworm. And the interesting thing is that all of that work that we did 10 years ago and that nobody was really interested in is kind of resurfacing now, because I am using that information in our breeding program for organic farming systems. So we also want to make corn resistant to Western corn rootworms. And Western corn rootworm, and I'm not sure whether everybody knows this, but this is the most important pest of corn in the US, and I guess
it's one of the big ones in Canada as well.
Yeah, and so organic farmers have no options, have no transgenic options, so we need to develop some organic solutions, and native resistance is definitely on top of the list, and that actually brought me back to all the stuff that we worked on 10 years ago. And you asked, what are the resistance mechanisms, isn't it? So what are the what methods does corn use in order to protect itself? And this is there are different resistance mechanisms. One is tolerance. And tolerance means that the plant is definitely attacked by the insect, but can outgrow the damage and can produce still a sizable yield. Then there is antibiosis. This is the type of resistance where the insects, attack the plant, but the plant has a mechanism to fight the insect. So the insects that are feeding on the plant have, suffer because the tissue might not be as nutritional as nutritious, or there might be some toxins produced by the plant that negatively impact the growth and development of the plant of the insect. And then there is also antixenosis, and this is when the plant produces a kind of volatiles that are or have other characteristics that prevent the plant, that prevent the insects from starting to feed on the plant and to damage it. Sometimes for other insects, plants have, insects will avoid certain plants because they have plant hairs, and these are not, plant hairs are kind of not attractive for insects. They try to avoid that, and they are leaving. So these are the three resistance mechanisms that we also see in corn against the Western corn rootworm. So there are plants that are resistant to Western corn rootworm feeding because they can outgrow the damage. So they are so vigorous that they can produce a new root system after the insects feed on it. There are other plants, other genotypes that produce some chemical compounds that are toxic to the insect, or that are kind of, the tissue as a whole is not as nutritious to the insect, and they are not developing as quickly, as rapidly, or as vigorously as with a susceptible plant. And then there are also plants that produce some deterrents, And so with corn, we see all of these three resistance mechanisms against the Western corn rootworm. And that reminds me, sorry that I'm rambling here, but perhaps your audience doesn't really know what the Western corn rootworm does to the plant. So the Western corn rootworm, adults lay eggs into the soil in the, after they finish their developmental cycle in the summer, and the eggs overwinter in the soil. And then when the next year, when the corn is planted and the corn develops, then also the ears, the eggs of the plant, the larvae hatch and start feeding on the roots, and the damage can be devastating. Yeah. So.
So among those mechanisms, which seem to be most effective, the volatile compounds that deter the insects, or the toxins within the plant, or the general outgrowing? Which one seems to be the most aggressive?
I think in corn, we are looking at the native level of resistance then, and compare that to the BT resistance, for example, the BT transgenic resistance, then we recognize that the native level of resistance in general is much lower. So, however, one second, could you stop play recording, please?
All right, let me just pause this for a second.
Yeah. Yeah, so the level of native resistance in general is relatively moderate compared to transgenics. However, and I have to qualify that, we haven't really started breeding for Western corn rootworm resistance yet. So I think over the years, using modern technology, using molecular markers, genomic selection, we definitely are able to increase the level of native resistance if we really start doing that. With regard to, when we compare tolerance to antibiosis and anti-cystinosis, then I think in most of the germplasm, we see actually tolerance and antibiosis occurring as a kind of a mix. So we see that some genotypes have antibiosis. So the larvae starting feeding on the roots, have a kind of they suffer by doing that. And in addition to that, the plants can outgrow the damage very effectively. So there's this combination of tolerance and antibiosis. And often it's very difficult when you're doing field experiments in order to determine what is tolerance, what is antibiosis. You can't really, separate these. Then you mentioned volatiles. Volatiles are very interesting and exciting because studies shown also by my co-authors that, of these two papers that you mentioned, they were also investigating nematodes in the soil. And there are nematodes that feed on Western corn rootworm larvae. And these larvae are attracted to the plant by volatiles that are released by the plant when the larvae are starting, when the Western corn rootworm larvae are starting to feed on the plant. So, and this is a resistance mechanism that is started to be researched in more detail very recently. Actually, I heard a colleague talking about this at our agronomy day at the University of Illinois a week ago. And there is a new project that is funded by the federal government, I think the USDA here in the US, and they are figuring out whether it's possible to use that resistance mechanism in order to manage Western corn rootworms in the future. So nematodes might be the future for managing Western corn rootworm resistance.
Excellent. So that chemical compound that's released by the roots attracts the nematodes to kill the corn rootworm larvae.
Exactly.
Is that similar to how certain plants attract parasite wasps?
That's exactly the same thing. And the plants also do this. So after the larvae develop their cycle and the adults hatch and appear in the field, then they are starting to feed on the silk and also the tassel. They are feeding on the pollen. And the interesting thing is plants, or at least some genotypes, also release chemicals or volatiles into the air that attracts wasps, and they start to lay their eggs into the adult Western corn rootworm beetles. So the interesting thing about these resistances that we observed in corn against the Western corn rootworm is not only one single compound or one single gene that produces a certain response. However, there are multiple resistance mechanisms involved in general, and higher trophic levels are also involved. It's the nematodes that are called for help by the plant using specific chemical compounds, and there are volatiles released into the air to attract wasps to attack the adults. But in general, and I have to stress that the overall response, even though it's so complicated and also complex and exciting in itself, is not as effective as, the transgenic BT resistance. Perhaps I can, get on a tangent, on the sideline here. The interesting thing is that, why I am still interested in Western corn rootworm resistance, native Western corn rootworm resistance, is that this insect is very flexible in developing resistances to all kinds of management measures that farmers use to protect the corn crop. So, for example, there are populations that are resistant to organophosphates, that are chemicals that are used to manage these insects. There are populations that are, rotation resistance. So here in the Midwest, we have corn, soybean rotations, and these insects do not lay their eggs in cornfields, but lay their eggs in the soybean fields. And next year, corn will be grown there, and they have the right environment to thrive. And there are also now populations available or observed that are resistant to some of the Bt toxins that are used to manage them. And that makes them very interesting to study, isn't it? So the question is, why do these insects have the ability to develop resistances and adapt to management practices so rapidly compared to other insects? When you think about the European corn borer, for example, where we do not, observe, that level of adaptability.
If I may bounce in a quick second, I do know that at least in my neck of the woods, forage producers produce corn after corn after corn after corn very quickly. So I think that might contribute a little bit, but that's just my speculation.
Yeah.
But on to the next question. There were, in one of your experiments, you have found that the cultivars SUM2162 and SUM2068 seem to be the most resistant to Western corn rootworm. Do you have any speculations on to why or how?
Oh yeah, so when you have a closer look at the paper, then you see that we are, using several traits or phenotypes to characterize the level and type of resistance. So we are looking, for example, so we are excavating the plants in order to look at the root damage. So we are rating the root damage. We are also rating the level of regrowth after the Western corn rootworm larvae damaged the root system. So these are, these are traits that tell us something about the level of antibiosis and also the level of tolerance. However, if we really want to determine, the level of antibiosis, we also have to look at some larvae characteristics. So not only at the corn characteristics, but also we have to study the larvae. How do they respond to feeding on certain genotypes? So, and I think for that project or for that experiment, we also collected larvae and also adults that hatched during the growing season. And we evaluated their weight. And we also evaluated for the larvae their weight and the width of their head capsule in order to determine, how fit are they, how well were they developed at certain growth stages of their development, and so on. And when we are looking at the larvae that were recovered from these two cultivars, the SUM cultivars, then we recognize that the larvae were significantly retarded in their development compared to all the other larvae that we obtained from the other cultivars. That told us that here specifically the antibiosis plays a very important role. So there are some compounds in the tissue, in the root tissue of these cultivars that muted the development of these larvae. And so therefore we thought that, we saw this level of antibiosis, this level of, retarded development of the larvae was pretty unique compared to all the other cultivars that we screened over the years. So we thought that these cultivars are very special. So they are very special and worth investigating more in order to determine what the compounds are that actually cause that increased antibiosis.
Thank you. Now on to the second half of the questions. So the first one should be a quick one. What is top crossing?
Oh yeah, so you say this is a quick one, but as a corn breeder, we can discuss that forever. The thing is, farmers grow hybrids, and hybrids are crosses between two inbred lines. And inbred lines, as the name suggests, they are inbred, and hybrids are, show hybrid vigor when two inbred lines are crossed. In the breeding program, when we are developing inbred lines, then we have one problem. And the problem is that the performance of an inbred line, so the per se performance of an inbred line, does not tell us how it will perform in a hybrid combination. So when we have no idea how this inbred line will perform in a hybrid. So the correlation between hybrid performance and per se performance is very low. And therefore, we have to evaluate these inbred lines in a hybrid combination. We have to cross it with another inbred line. And in general, we do this at an early stage of our breeding program by using one inbred line from another heterotic pool as a parent to test all the inbred lines that we developed in one other specific heterotic pool. So the thing is, we need to evaluate an inbred line as a hybrid in order to determine its worth for carrying it further in the breeding program. And therefore we evaluate it as a hybrid. And that is a top cross. Yeah.
Thank you. Carrying on from that, why did resistance to corn rootworm appear to be passed on in some inbred cultivars while not in other inbred cultivars?
Yeah, so we found that, as I mentioned, as an, resistance mechanisms in cultivars is kind of a mix between tolerance, antibiosis, and anticyanosis. And I think when we are looking at inbred lines, then, we will not see a lot of tolerance because these inbred lines are showing inbreeding depression. Okay. When we are testing these in hybrids, then we also see, much more, vigorous development and growth. And that also translates into, increased tolerance. And I think this is part of the explanation that explains why we see that hybrids perform in a certain way and inbreds perform in another way. So the correlation between the resistance at an inbred level can be very different when we look at the level of resistance of that inbred in a hybrid combination, because we add this additional vigor to the plant. And in addition, so this is one reason, and thinking about it, when you're creating a hybrid, you can also combine different types of resistances into the hybrid, isn't it? So you have one inbred that has shows one resistance mechanism, and you have an inbred that shows another resistance mechanism or a higher level of resistance. And then if you combine these, then hopefully these resistance mechanisms also combine and cause a better, higher level resistance response to the Western corn rootworm.
So if I'm getting this correct, you have to stress test the plants by crossbreeding them to see if they actually pass on their traits, because not all their traits could manifest.
Absolutely, yeah. So if you cross moderate resistant Western corn rootworm inbred line with an inbred line that is a high performing inbred line in hybrid crosses but does not carry any resistance, then you definitely dilute the level of resistance if it's not a dominant trait. And all the all the Western corn rootworm resistances that we evaluated are all quantitative. That means there are a lot of genes that are contributing to the level of resistance. It's not one or a few genes that are causing the resistance. So therefore, we have to deal in our breeding program for Western corn rootworm resistance with a trait that is highly complex. Hundreds of genes are involved, and every gene contributes only a tiny little bit to the resistance.
All right, one more question. This is more of a broad question, so you can feel free to answer as much as you want. I've noticed that there seems to be a lot more focus on single gene traits, either through genetic modification or through single gene mutations that add a lot of resistance to the plant, like say the scab resistant gene in apples.
Mm-hmm.
Do you think that's a bit too much of a crutch? Should researchers focus more so on breeding for multi-gene traits, or keep on staying the course?
As a plant breeder, specifically when you're working for a company, you want to make quick progress, and you always hope that there are single genes that can have a major impact on the trait that you want to improve. Because if there is a single gene that has a huge impact on the trait, it's very easy and simple to manipulate within your breeding program. And you can even apply modern technology like genome editing in order to advance quickly. But also if you apply conventional breeding methods, this is then relatively easy, because a single gene trait can be observed phenotypically, or if you apply genomic selection or marker-assisted selection methods, you can make rapid progress. So therefore, as a plant breeder, you definitely want to work with single gene traits. However, I think that a lot of traits that are of economic importance are quantitative. When you're looking at corn yield, for example, there's not a single gene that confers high yield or that will increase yield, tremendously, or that you have a step improvement. So we are constantly improving these characteristics. We are constantly improving in corn yield, but this is by changing, gradually all the genes, or selecting for all the genes that have an impact on that characteristic. And there are many genes, for example, for grain yield in corn that is highly quantitative. And for the Western corn rootworm, as I mentioned, a single gene characteristic, a single gene disease resistance, like the Bt resistance, is very effective in Western corn rootworm, or against Western corn rootworm. However, it puts the insect also under tremendous selection pressure. And interestingly enough, there are resistance genes at a low frequency in Western corn rootworm populations that then they are selected for the increase in frequency, and suddenly the Western cornworm population is resistant, and the BT and the BT gene is not effective anymore. So this can actually be prevented if we, decide to improve the more quantitative level of resistance, like the type of resistance we were working on, because it is very unlikely that the Western cornworm beetle is able to adapt, to this very broad quantitative type of resistance, where there are multiple genes are involved, and the insect has to respond to each of these genes separately. So the probability of adaptation is pretty low. So perhaps it's, if you focus on Western cornworm resistance, a combination of a moderately broad-based quantitative genetic resistance background in corn, to which then the highly effective BT resistant genes are added, might be a good solution.
Yeah. Thank you. And this will conclude the interview. So any last thoughts you want to give out to our audience?
Oh, that's even a more broader question. so I think, with regard to, I think this is focusing on Western cornworm, isn't it? And I think looking at the Western cornworm, we learn a lot about how to manage insect pests, and what to do and what not to do. And we've recognized that BT is a very important tool in our arsenal of fighting that insect that is so devastating. However, we also recognize that this insect has an incredible ability to develop and to adapt to adapt itself to all of these transgenic events. And we need to learn, looking at that what we did in the past, that what's going on in the future, to find ways of managing it. Could we cut that? I think this was rambling and it doesn't make any sense. Can I say something else and you bring this together?
I'm not good at that whole cutting thing, but I think I can. Okay. I think it'll work.
Okay.
You made sense to me.
Okay. So and I think climate will change in the Midwest. I think here in the Midwest we will get warmer, and the winters will get milder, and I think we will see more insect pests popping up. And so that means new insect pests will develop over time. And I think we have, so we need to develop all our tools. So we have to develop quantitative resistances or native resistances, and we have to develop these transgenic resistances in order to be able to manage all these pests that will come towards us in the future.
Thank you. You've been an awesome interviewee.
I'm not sure. I'm rambling.
No worries. That's what you're here for.
I'm very excited about these things, and